Have you ever thought about how we can build smarter, greener buildings? And I'm not just talking about slapping solar panels on the roof. I mean changing the very stuff we build with. Well, today we're going to dive into how scientists are creating digital blueprints for brand new materials and then testing them like crazy before a single brick ever gets laid. Let's jump in.
Okay, so first up, I just want you to look at this number, 40%. It's a massive chunk of something. Any ideas? It's a number that has a huge impact on all of us, every single day, whether we're at home or in the office. You got it. That 40%, that's the share of all energy our buildings can chew through in developed countries. The places we live and work, they're some of the most energy-hungry things on the entire planet. And that, right there, brings us to the heart of the problem we're digging into today, the giant energy footprint of all of our buildings. And it is a problem that we really can't afford to just ignore.
So let's put a few more stats on this, just to see the scale. The source material points out that buildings can use up to 40% of all energy in developed nations. And on a global scale, the building sector is on the hook for about 30% of all energy-related CO2 emissions. So you can see why making our buildings more efficient isn't just a nice idea, it's an absolute must for the climate.
But what if we could build walls that actually work for us? Walls that help keep our homes cool in the summer and warm in the winter, all without using extra energy. Let's take a look at a potential solution that's kind of like a magic thermal battery. So this magic is a real thing. It's called a phase change material, or PCM for short. The easiest way to think about it is like this. Imagine tiny little beads of wax mixed into your drywall. When the day gets hot, that wax melts, and in the process, it soaks up heat from the room. Then when things cool down at night, the wax turns back into a solid, releasing all that heat it stored. It's literally a thermal battery that charges and discharges with the daily cycle of temperature. Now let's see what that actually looks like in practice. On the left, you've got a normal wall. A hot day comes along and the heat just punches right through, warming up the inside. But on the right, with the PCM-enhanced wall, it's a whole different story. The PCM layer grabs that incoming heat, melting to absorb the energy and keeping the room cooler for a lot longer. Then at night, it releases the heat when it's cool outside. It basically shaves the peaks off your heating and cooling needs.
It sounds amazing, right? A total game changer. But, there's always a catch. How can you be sure this will actually work in a real building, without spending millions to build it first? This is where we hit the big digital simulation challenge.
This quote from the source material really just nails the problem. The very thing that makes these PCMs so useful, that sudden jump from solid to liquid and back again, is a complete nightmare for computer models. It's not a nice smooth line, it's a sharp, sudden change that is incredibly hard to predict accurately.
And that leads us to the million-dollar question. Literally. How could an architect confidently design with a new material like this? They need to know for sure that it's going to work. What they need is a trustworthy digital twin, a computer model so accurate that it's like having a perfect virtual copy of the real thing.
So how do you build that kind of trust in a computer model? Well, you don't just ask nicely. You make it run a gauntlet, a punishing 4-step series of tests designed to prove it's the real deal, following a process that's a lot like the industry standard for this kind of thing. These are the 4 trials it has to survive. First, does the model's math actually match up with a real-world material? Second, does it follow the basic laws of physics? Third, how does it do when you put it head-to-head against another simulation in a realistic setup? And fourth, the final boss. Can it predict what happens in an actual, full-sized room?
All right, let's start with step 1, the reality check, or empirical validation. For this, the researchers took actual lab measurements from a real-world PCM, a paraffin material called RT27. Then they tried to see which of 3 different mathematical equations was the best fit for describing its real-world behavior.
And the results? Well, they speak for themselves. The R-squared value you see here is basically a goodness of fit score, where a 1 is a perfect match. And as you can see from the table, the arctangent function was the clear winner, with a score of almost 0.99. The model's core math was now officially grounded in reality.
Next up, it's time for the physics exam, analytical verification. This is where the model had to solve a classic problem straight out of a textbook, called the Stefan problem. It's basically about simulating how something like a block of ice would melt under perfect ideal conditions.
It's a pure math test to make sure the model hasn't forgotten the fundamental laws of heat transfer.
Okay, now things start to get a lot more like the real world with comparative testing. This time, the model had to simulate a complex wall with multiple layers: gypsum, insulation, the PCM, and an outer board. Then, its results were put head-to-head against another previously validated simulation to see if they both came to the same conclusions.
And one of the key findings from this test is right here on this chart. It shows how well the PCM layer cuts down on the peak flow of heat trying to get into the building. And what's super clear is that the thicker you make that PCM layer, the better it works. The model was successfully predicting realistic performance.
And that brings us to the final trial, the ultimate test. Step 4. All the theory and comparisons go out the window. Now, the model's predictions had to go up against cold, hard data from a real, full-scale experimental room called Minibat. Could the digital twin actually predict the surface temperature of a real wall in the real world?
And the verdict? A huge success. The model ran the gauntlet and came out the other side. Its predictions for how the wall's temperature would change throughout the day lined up almost perfectly with what the actual sensors in the room recorded.
And here's the final proof. Just look at these scores. An R-squared value over 0.93 means it's an excellent fit with reality. And the RMSE, that's the root mean square error, shows that the average error was less than 1 degree Celsius. I mean, that is an incredibly accurate prediction. The digital twin was now officially trustworthy.
So what does all this intense testing really mean? It means we can finally bridge that gap from a really powerful computer model to a powerful tool for the real world. Because this model survived every test thrown at it, it's no longer just an academic exercise. It's a trusted tool. It can now be built into big-time building simulation software, like Modelica's AixLib library. So now architects and engineers can design with these advanced materials and be confident that what they see on the computer is what they're going to get in reality.
All right, so let's wrap this up. What are the big things to take away from all this? First, our buildings are a massive part of our energy and carbon problem. Second, cool new materials like these PCMs, these thermal batteries, are a brilliant part of the solution. And third, and maybe this is the most important part, if we want to build digital tools we can actually rely on, we have to put them through an incredibly tough, multi-step validation process. No shortcuts.
And that leaves us with one final thought. We now have these incredible digital tools that can design and test super efficient buildings with unbelievable precision before we even break ground. The tech is here, so the real question is, what's stopping us from using it everywhere?